Good day, good people of SEOF. Today we will be looking at retinal histology, and I want us to approach it from exterior inwards. That is from the retinal pigment epithelium to the internal limiting membrane. But before that, I need to say that retinal pigment epithelium, which is the first layer of the retina from the exterior, has a very good close relationship to the choroid. In fact, there's what is known as Brooks membrane or RPE Brooks membrane complex, which is actually an association of tissues between the outer end of the retinal pigment epithelium and that of the early or innermost tissues of the choroid. This close association is very important in that if we remember that the outer retina is actually supplied by choroidal circulation. So the retinal pigment epithelium and other tissues of the outer retina actually derive their nourishment from the choroidal circulation. Then coming to the retinal pigment epithelium proper, which is the first layer of the retina from exterior. It's a single layer of cuboidal cells that make it up, which is melanin laden. That's why it's called pigmented, that's why it's dark. The melanin serves a very useful function in that it absorbs the light that comes into the eye first, and this prevents phototoxicity of the retina, and more importantly prevents reflection of the light, which would have hindered proper perception of images and clear vision. It's also important to note that this retinal pigment epithelium has tight junctions which form the outer retinal blood, retinal barrier. This is important so that it is not all the solutes, molecules, toxins that come through the choroidal circulation that has easy access into the retina proper. We also remember that the retinal pigment epithelium nourishes the outer retina and phagocytizes the photoreceptor outer segments, thereby replenishing them from time to time. So it essentially nourishes the outer retina and clears wastes from the outer retina. This is why its function is so important. Anything that affects the retinal pigment epithelium, a fairly large section of it, is almost all the time it will affect the proper function of the retina. It's also important to note at this point that retinal pigment epithelium has a rather loose association with the neurosensory retina. There's a potential space between them actually, which is maintained by a loose association between retinal pigment epithelium and the photoreceptors. Then the pressure that comes from the vitreous end of it also maintains this space, a potential one, in normal situations. But there are other abnormal situations where this potential space becomes a real one, and there'll be a collection of fluid there, which may range from serous fluid to blood and all whatnot. That's actually what happens in retinal detachment. The next layer after the retinal pigment epithelium is the photoreceptor layer. This is the layer that contains the photoreceptors, which are the photosensitive cells proper, that the first cells that are involved in the phototransduction of light stimulus into images. There are essentially two types of them. We have the rods photoreceptors, which observe vision in the dark or dim environments, and they are located mostly mid-peripherally and peripherally. That is why mid-peripheral and peripheral diseases tend to affect night vision first. If you remember, retinitis pigmentosa is a typical example. And if you also do pan-retinal photocoagulation and knock off most of the mid-peripheral and peripheral retina, they also have some issues with seeing in the dark. While the cones, which are the second type of photoreceptors, are concentrated in the middle, the area I earlier described in the anatomy as the posterior pole or the anatomist macula, the area enclosed by the temporal vascular arcade. That is where the cones concentrate, especially in the macula. Macula is essentially a cone-laden area, which is why it subserves vision, acute vision, and the cone's function is subserving vision in the day and color vision. So it follows that when the cones are affected, central vision is affected, color vision is affected, and vision during the day is affected. You also remember that when central vision is also affected, reading is affected. The next layer of cells is the external limiting membrane. It's actually the end of molar cells that join together to form that. It's not a ray membrane really, but that's the way it's described, the external limiting membrane. The molar cell, we'll remember, is the supportive cell in the retina. Just like we have in the CNS, we have fibrous astrocytes, protoplasmic astrocytes, oligodendrocytes, and ependymal cells. The molar cell is the supporting cell of the retina. So it spans through almost throughout the layers of retina, ranging from that external limiting membrane to the internal limiting membrane. The next layer after the external limiting membrane is the outer nuclear layer. This contains the nuclei of rods and cones. After the outer nuclear layer is the outer plexiform layer. This contains the nervous fibrous processes or connections, synapses, that is communication fibers between the photoreceptors and the cells in the middle of the retina, namely amacrine, bipolar cells, horizontal cells. So that is the layer that contains fibers with which these two layers communicate. That is now on the photoreceptor layer and the horizontal amacrine bipolar cells. After the outer plexiform layer, going inwards, is the inner nuclear layer. This is where the cell bodies of these cells, I mean bipolar, amacrine, horizontal cells, and also the cell body of the molar cell is located here. These cells are the cells that process the nervous signals once it comes from the photoreceptors. They are the first group of cells that process the nervous signal for onward transmission to ganglion cell. The next layer after the inner nuclear layer is the inner plexiform layer. Again, this contains the fibrous nervous connections or synapses between this group of cells that process nervous signals first and the ganglion cells proper. After this, you meet the ganglion cell layer. After the ganglion cell layer is the nerve fiber layer. Nerve fiber layer are actually essentially the axons of the ganglion cells. So they aggregate in the nerve fiber layer and they all run towards the disc, depending on which part of the retina they are coming from, but they all run towards the disc. Because of this, their thickness is largest just before the disc, because that's where the aggregation from all parts happen. And this can easily be noted on OCT. In fact, it's one of the things you can easily use to know whether which part of the eye you're dealing with when looking at an OCT report. And it can also help you, guide you together with the location of the macula, whether you're dealing with the right eye or the left eye. The last layer after the nerve fiber layer, which is abutting on the vitreous, is the internal limiting membrane. This is a basement membrane that's elaborated by the footplates of the molar cells, and some of the footplates actually get into that layer. It's essentially a layer of the footplates of the molar cells and the basement membrane they secrete or elaborate. It's a thin, fairly tough membrane, very thin in normal under normal circumstances, but can become thickened and more obvious, especially on OCT, in disease conditions like in epiretinal membrane. It becomes more thickened and hyper-reflective on OCT, and it can actually be peeled off surgically. Most times it's the first step in most vitreoretinal surgeries, especially where vitrectomy will be done, or in macular hole surgeries. The first thing they usually do is to do internal membrane peeling. So it can actually be peeled and it becomes an obvious membrane that can be seen. It is worthy of mention that the vascular supply of the retina, there are two essential vascular plexuses: the inner one, or the more major one, which exists in the nerve fiber layer, and the other one, the smaller plexus, which exists in the inner nuclear layer, from vessels, branches sent down from there to the nerve fiber layer. That is why when there is a rupture of those vessels or disease processes where they start leaking whole blood, they are found in nerve fiber layer. And because the nerve fiber layer is a tightly packed layer, they don't have space with which to spread evenly, so they get spread like a tongue of fire. That's what we describe as flame-shaped hemorrhages. So flame-shaped hemorrhages are found in the nerve fiber layer, and because the nerve fiber layer is horizontal in nature, so those blood, they have to spread horizontally. They don't have access to going down. But if the bleeding happens in the inner nuclear layer or lower layers, the cells are arranged in columnar fashion, so they have more space there. So looking at it ophthalmoscopically, it will rather appear almost roundish, and because it's coming from inside, it has more space. So that's where you have dots and blot hemorrhages. So the point to note here is that flame-shaped hemorrhages happen in the nerve fiber layer, while dot blot hemorrhages come from the inner plexus. Thank you very much. I think we're going to call it a day at this point. Thank you.